Good afternoon. It's really an honor to be here. I did machine learning summer school in 2007 at Toronto. It was much, much smaller. I think there were, I want to say 10 people, maybe 15 people there. All of us went on to be faculty. I don't know what that means. Either the instruction was particularly good or it was the right time to be in the field. Anyway, it was huge then, and I hope that it's just the same for you guys here. I wish you all the luck you can have. Okay, so I typically stupidly bite off more than I can chew every single time I get an opportunity like this, which thank you for the organizers for giving me this opportunity. And of course, instead of just doing probabilistic programming or just doing Bayesian nonparametrics, I'm going to try to do both of which are far beyond the space allotted. So I'll probably not do any of the subjects real justice, but I'll do my very, very best. The other thing that I should say straight away is that I sent out an email to all of you this morning that had a couple of links on it. I think probably the most important sort of take-home, the most important material that I've developed for you guys are actually the practical exercises and the artifact, which is the website, which is basically developed for this course, so that you can go home or during your break times when you're not drinking or eating whale meat, you can continue to develop your understanding of probabilistic programming. I also, in my own teaching, when I teach in groups this size, I know that it usually takes maybe around about a week for people to come around to my style of lecturing and preference for high levels of interactivity. I don't know how this summer school has been going so far, but I really like interactivity, and I will beg for it from you. And if I don't get it, it's going to be miserable for me, and it's going to be miserable for you. So. So please engage with me. I'll do my very best to answer your questions. I'm guessing that many of you could answer questions that I would have a hard time answering, and that's great. Please interact. I promise not to make fun of you. In a group this size is very, very intimidating to put your hand up. The stuff that I'm going to be talking about, particularly with respect to Turing-complete probabilistic programming, is very confusing at some points, and you will not be alone in sort of not understanding what's going on at points. So please help me explain. Can I just see a show of hands also real quick on sort of like background, just so that I have an idea of how much time to spend where? How many of you have ever programmed in Lisp or Scheme? Okay, fair. Actually, a surprising number. How about Cloture? Just for the fun of it. Okay, so okay, great. I'm not going to make you program in Cloture. I will say, though, that as we go through, and I'll get into it in just a second, as we go through the tutorial, you'll have an opportunity to sort of engage at multiple levels, either as a user of the system or as a developer of the system or as somebody working on mathematical methods or that sort of thing. I'm going to try to point out all of these opportunities to you. And one unique opportunity that I can give you, and I'll talk about this in just a second, is that I can give you access to the source of one of these probabilistic programming systems if you want to look at it. And what I'll be talking about is written in Cloture, which is a programming language apparently not many of you have heard of, which is a scheme on top of the JVM. Anyway, okay, so that was a lot of words for a very, very boring title slide, so let's get into it. I should also point out that there haven't been a huge number of tutorials written on probabilistic programming, and there are many other people who could give this tutorial, and there are people that you'll see showing up throughout the talk, and it's worth knowing who they are, and it's worth pointing out that you should probably pay attention if you get interested in this area to their work. In particular, my group is this top three here. Jan Willem van de Mink is a postdoc of mine who is actually the lead developer of the probabilistic programming system I'm going to talk about. Brooks is a PhD student working with me on Probabilistic-C. Somebody that you'll definitely want to interact with is Jura, who's just there. very kindly agreed to come with me and help you with technical issues and understanding and so on and so forth. So for all intents and purposes, think of him as a TA for this section. He's also designed the hardest homework problem, or helped me answer the questions on the hardest homework problem having to do with Bayesian nonparametrics in probabilistic programming. So he's a good intellectual resource as well, and was one of the developers of one of the original probabilistic programming, or one of the current probabilistic programming systems. Vikash is a research collaborator. We're on a DARPA program together. Abhi was a professor at Harvard. He's written a couple of probabilistic programming systems. Vikash and Noah wrote Church together. These guys are, Andreas Stuhlmuller has a bunch of interesting examples I'll point out later. Dan Roy was in the original Church paper. Wingate has written some very, very nice, very efficient inference engines for probabilistic programming. And of course, you probably all know Stuart Russell, who's among many of the other things he's done, is responsible for blog. So you've had at least one sort of lecture on something that could fall in the class of what I might call probabilistic programming systems. But let me give you my take on what probabilistic programming is, and how it fits in with computer science and statistics. So in computer science, and when we're writing programs, we're generally speaking, we write a program. It's in some sense given. We generate it, right? We write it down. There's a program. It has some sort of parameters, arguments, whatever you want to call them, and we also provide those to the program. Then we execute the program to get some output. Okay, so these are given. This is generated. Yeah. Okay. In statistics and modeling and whatever, we generally have a problem setup that looks like this. We have some data. The data is given to us, and we write some sort of generative description or model of the data. And what we want to do instead is invert that somehow, right? Figure out what settings or distribution over settings of the parameters, when passed through this generative model, could have given rise to the observed data. Okay, it's a pretty general formulation of what's going on in statistics. My view on probabilistic programming, or one view on probabilistic programming, is that it's the computer science generalization of this sort of statistical problem-solving, modeling approach, which is to say that what you're given are data, observations. They're output from some program. Okay, you're also given the program, i.e., you write your model as a program. Okay, not as a set of equations, but instead as an actual program that generates data. That program will have some variables in it that you actually don't really know what the values. You don't really know the values that they should take. You don't know what those constants are exactly, or the number of variables may be, or something like that. And what you would like to do is, given the observations, sort of invert the program and figure out what settings of the parameters, or more generally, distribution over the settings of the parameters, could have given rise to the observations were you to have run the program with those variables in the first place. Okay? All right? Okay. The goals of probabilistic programming, as I see them, are kind of broad. Okay, I'm in this because UI pointed out that I've done a bunch of stuff. It's kind of true, and it sort of depends on what you're really interested in. If you're really interested in doing statistics, or you're trying to solve AI kinds of problems, or if you're trying to get a job at Google, the kinds of things you're going to do are a little bit, they vary. Okay, so I'm into the AI thing. I'm working really, really hard at that. So I moved into probabilistic programming because I think it's the best path towards that, basically. But the goals of the probabilistic programming community encompass that and a couple of other things. So from a practical perspective, if we are to succeed in the field of probabilistic programming, then the tools we build should dramatically accelerate iteration over models. And the second homework or second exercise homework that we designed for you, third, we'll sort of stress this. Okay, so instead of writing down a bunch of math and then deriving inference equations and then writing code that's probably buggy and then checking to see what the answer looks like and so on and so forth. You just write your generative model as code, and you write a program. And if everything were beautiful and absolutely perfect as we see it possible in the future, then inference is completely automatic. Okay, so inference is provided for you. You write your model, inference is provided. And my hypothesis, and I think this is fairly reasonable, is that writing generative code is certainly easier than deriving model inverses. Okay? Okay, that's like not a whole lot of fun. We have done it. I've done it thousands of times. You guys have done it probably as many. And of course, this is a questionable audience for promoting probabilistic programming. Okay, because you guys are all getting PhDs that make you experts in line 2, basically, or are already experts in doing this. So you might not appreciate that, in fact, other people would be able to write models that are effective without actually having to pay you 100,000 currency units per year to invert the mathematical equations that you wrote down that may have something to do with the generative process that they're interested in. There are lots of qualifiers there. But if we succeed, writing programs is a heck of a lot easier than doing math. Okay? Where I think the community does plug in is that although, depending on exactly how you define probabilistic programming, and I'm going to stick with Turing-complete probabilistic programming, which I'll distinguish from the rest in a bit, inference is hard, but it does generalize and actually support the solution to a very broad set of problems. Okay? So if you're working on inference, I personally am not that terribly interested in inference papers that take a model and show that you can do inference in that model better. Okay? Unless that model is very, very widely applicable, which there are many of, regression, classification, blah, 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 blah. But this is probabilistic programming offers the possibility of thinking about programs, the set of generative models written as programs, as an abstraction layer against which new inference procedures can be tested. Okay? So there's an abstraction layer. Models in a language, interpretation of those models in a probabilistic programming way is inference. So if you want to develop and test new inference algorithms against a broad set of models, the broadest possible in some sense, then you should probably work on inference and probabilistic programming. Okay? So in that sense, though, it seems a little bit less sexy because inference procedures become compiler optimizations. You actually sit below a language barrier. It's hard work, but it's very rewarding because if your inference procedure is better or faster in general, then automatically you get applicability to a very, very wide set of models. This is maybe the most controversial goal, which is to enable the development of more expressive, or I don't know what expressive means, we use that word a lot, more expressive models. So probabilistic programs, the way I'm going to talk about them, can express a superset of graphical models. Okay? Modern machine learning models are very, very short. You can express, you'll see in homework 3 and homework 1, whatever, that the typical models that you would spend thousands and thousands of lines of code writing, you can write very, very efficiently in these languages, which suggests that if you were to write longer programs, they would be more expressive in some sense. But also, there's sort of a flip side, which is, why at some high level do we use the models that we do to model phenomena of interest? Is it because we've happened to find inference procedures that make those models easy to work with, or is it because those models are actually appropriate to the domain, right? So I find myself, when I'm doing applied work, taking whatever problem I have and mashing it onto logistic regression, or mashing it onto an SVM, or mashing it onto an HMM in some sort of a way. Whereas I might have a heck of a lot more prior information that I could stick into a generative procedure that describes my data, right? And if maybe there's the possibility that, in fact, I could write a completely different model that actually works in a probabilistic programming system, that's much more expressive or is more statistically efficient, and doesn't fit with the current set of models for which inference is already known to be good. Now, it's a possible. I don't know if that, did that make any sense what I just said there or no? I sort of like lost my train of thought in the middle of saying what I was saying. That was a question, nobody answered it. Did that make sense? Yeah? Okay. I can't remember the beginning of what I said. I'm old, sorry. It's okay, you can laugh at me too, it's fine. Happens a lot. Okay, so we'll pick up speed a little bit. So the 3 lectures are really going to be 2¼ lectures, probably. The first one is today, we're going to talk about programming. Okay, so this is going to look at probabilistic programming from the user perspective. Okay, so how would you interact with the system? What do you use? Let's get into it. Let's think about what it is we're doing and try writing some programs. Tomorrow morning we'll do understanding, which is to say we're going to do some stuff that's going to be a little bit confusing. You're going to write these models and you think, how the heck are you doing inference in this? Or you'll think, I understand how you're doing inference in this, and you won't. Okay. So we'll do understanding in the first lecture, and then we're going to spend the third one together, jammed in little groups, working out a Bayesian nonparametric practical application kind of problem, which is just, again, a learning experience in the system. So today's programming, and then understanding and tutorial, sort of practicum in the third lecture slot. I would like to do that together because we can do a lot of interaction there. So I don't know if you guys have grouped up and friends and that sort of stuff, but make sure you're not alone for the third lecture. You will not get very much out of the third one unless you actively participate in the solution of the exercises that I provided for the first 2. The first 2 exercises are relatively straightforward. You should be able to actually complete them in a relatively timely way and give yourself plenty of time to drink tonight. But the third one will stretch you a little bit. Okay, so today I'm going to just talk about systems a little bit. Then I'm going to talk about kind of a problem template, which will give you one way of thinking about what we can do in probabilistic programming. Then I'll go through the system that you can use to solve all of the exercises, which is called Anglican. We'll talk about the syntax of Anglican, talk just a little bit about its semantics, do a couple of simple examples so that you can get going quickly, talk about how to interpret the output of the system, discuss limitations, of which there are currently very, very many, give you a little demonstration, race you against the computer in an inference exercise, and then introduce the exercises. Okay, so probabilistic programming systems. There's a little bit of confusion about nomenclature in the field currently. I'm not the one to probably resolve it. I'll try to distinguish systems on this slide and then move on. So I would call the first set of them application-driven, maybe model-driven. They are either inference procedure specific or model family specific or something like that. So you may know bugs and jags, where you can write down a description of a model and then perform inference on it automatically, but these usually are graphical models. Stan, of course, any hierarchical Bayesian model with continuous and differentiable, that's continuous, that has continuous parameters and is differentiable with respect to those parameters. You guys have played with that. Infer.net is basically message passing on a factor graph. There are some other languages. Eyeball and Figure, Avi Pfeffer has done great work with those, and Blog, which you may or may not be familiar with. It's a first order open world probabilistic programming language, probabilistic logic. And then there are these, what I would call Turing-complete languages, and these are the ones that are of interest to me because of their sort of AI implications and cognitive science implications and the fact that they generalize inference over a very, very broad family of they allow you to ask lots of questions in a unified language, I think is one way to say it. So you could argue that Church's was the first paper that really pushed this concept. It came out in 2008. There's an archive paper in 2012 with some updates. There's been some follow-on work to Church. In particular, Church was very elegantly pitched as a language for generative models. And they pitched it that way because inference basically didn't work. But there's been a bunch of work on inference in these kinds of languages. A very nice paper called it's a lightweight interpretation of probabilistic programs by transformational compilation by David Wingate. Sort of was the first step towards making church actually practical. A different approach that my group has spent a bunch of time developing just finally came out at this AI Stats. It's a related language called Anglican that does a different kind of inference. That different kind of inference has given rise to another language, Probabilistic-C, which might appeal to some of you. And then Venture, sort of at the same time, is approaching scalability and actual practical utility of these kinds of Turing-complete programming languages via a different sort of path, which I'll get to in a bit. Okay, so we're gonna focus down here on these. Anglican and Venture share more or less the same syntax. Church has a slightly different syntax, but I think if I kind of do my job right, you'll see that they're all the same, and you basically could end up programming in any of them after this. The challenges and expressivity of these languages are basically interchangeable. Okay, so Anglican. I sent you an email. How many of you actually downloaded Anglican? Wow, you guys are much better students than am I. I would never have done such a thing. Okay? I've been like, no. Okay. So, Anglican, a little bit of a, you can laugh at this. I'm going to make it an explicit joke. A Church of England venture. Okay, so it's, I'm obviously not English, but I teach at Oxford now. So both Venture and Church, Venture and Anglican are roughly speaking descendants of Church, and Venture existed before Anglican but didn't get published, and it has different variants. But anyway, the critical part is that the syntax and the modeling language syntax and semantics are actually more or less the same between Venture and Anglican, and in fact Venture in particular, Vikash was responsible for writing them down. So there's some syntactic differences between Anglican and Church, and Venture and Church. There are some semantic differences, but from the perspective of this list, you can sort of think of them as interchangeable. So there is a website. How many of you went to the website already? Obviously, you had to download it. Did anybody do anything other than download the code? What did you do? You ran a few of the examples. They actually worked? Oh, thank God. Okay. Okay. So there is a small group of people who are actually using this system now. Small. Okay. You guys are a pretty big multiple on the size of the user community. Okay. So that's both exciting and absolutely terrifying. I don't know how many of you have actually released code into the wild or systems into the wild, but I can tell you that releasing a programming language into the wild is more terrifying than any bit of bloated middleware you've ever coded for whatever project, okay? There will be bugs. You'll find bugs, almost certainly. We've done extensive testing, but that's not enough. 138 people will find more bugs than anyway. There is a public place that you can list issues. In fact, you can actually see the issues that as we've documented them, as they've arisen. Please, when you're using this system, if you find bugs or there are things you don't like, or there are comments you'd like to leave, so on and so forth, please make sure to leave them there. The developers, I actually coded some of the original version of Anglican, but it's long since been improved over what I wrote. Jan Willem van de Mint, my postdoc, you can find him easily on the web if you have questions or want to actually take a look at the code. He can definitely give you access. I can give you access as well. Yura is here. He knows what's going on. He's one of the lead developers now. And Vikash has, again, helped out a bunch with research collaboration on Anglican. Okay. So don't miss that, okay? It will be watched and responded to over the next couple of days very closely. Okay, what is Anglican? Anglican is a Turing-complete probabilistic research programming language. So it's research, basically means alpha, right? It supports accurate inference in programs that make use of complex control flow. What does that mean? It means we have if statements and branches and and not looping constructs, but recursion, essentially, including recursion, and we can deal with Bayesian nonparametric statistics, okay? What does it mean? It means that our programs aren't differentiable, basically, and they are allowed to have arbitrary amounts of randomness, which is going to be important for a number of applications. And you can actually use it. I sort of surprisingly find myself actually using it as sort of like, where it's at right now is, how many of you, when you have to calculate something that you don't want to calculate, open up MATLAB or an IPython notebook to add a couple of numbers together? How many else? Okay, that's disgusting, okay? I do it too. I mean, I have like a $7,000 calculator, right, if you count the machine and MATLAB, right? Okay, so I actually use Anglican for that kind of stuff now, okay, because it's interactive on the terminal. You can pipe commands into it if I want to, do a little teeny tiny inference problem like what's the mean of this if I put this prior on and I observe these little data points. That's the way to go, okay? Super fast, super easy, and very, very usable, okay? So for small models, where you'll start to discover the boundaries pretty quickly, you can actually use the system, okay? What did we do? Okay, we had the realization that this new approach to inference, particle NCMC, was actually applicable for probabilistic programming inference as well. Now, theory suggests that PMCMC, particularly particle Gibbs, has really, really nice convergence properties. Okay? So, first of all, the realization that you can actually do this in the probabilistic programming context is somewhat non-trivial, as you'll figure out. But once we realized that you could do it, then it was very exciting because, in fact, it has really, really nice convergence properties. Of course, probabilistic programming violates all of the theory related to that, those claims. But what we get is a big improvement in performance over a very, very wide variety of problems. So this is what I was talking about: is if you're going to work on inference, you work below the level. You can think of this as sort of proposing a compiler optimization for a probabilistic programming language. The techniques in Anglican can be applied to Church or Venture or whatever. In fact, have already more or less been integrated into Venture, although in a slightly different way. And what it does is it really does actually open up a path towards scalability of these systems. Okay, so it's very simple to implement. It only requires a simple machine layer abstraction, and it can scale to massive parallelism relatively straightforwardly. There are some research issues before we get there, but I digress. In fact, we've already sort of made a step in that direction. Okay. And even before I show you Anglican, I'll show you a follow-on, which my student Brooks and I worked on. And yes, that's the picture on his website. He actually has really nice hair. I don't understand why he would cover it up. But so the kind of techniques that I'll talk about allow us to do things like this. So we can actually, so let's look at this for just a little bit, take a little bit of time on it. So the techniques that in Anglican and the tools you're going to play with, and in particular the second lecture where we talk about how we actually do inference, will allow you to actually write a probabilistic programming system that looks exactly like this. Okay, so this is a C program. Who's programmed in C? Okay, awesome, good. Okay, so you know header file. Oh, there's a header file. That's our header file. Define a couple of constants, k and n. There's some matrix T, a transition matrix, A in the case of HMMs, if you're used to the standard HMM notation. There's some data. You could load that from a file if you wanted to. There's a set of initial states, or an initial state distribution, which is 1/3, 1/3, 1/3. There's a set of means for the observation distribution, 1, 1, 0. There's a main function. There's a set of states here, an integer array of states of length n. And what we do is for n equals 1 to n, we generate the latent state. We observe whatever data came out of that state, and then we predict the state that the system was in at that time. Okay? Now, what does this program do? there's some normal distributions in here, so there's a normal log probability here. So this is an HMM, okay? It's a hidden Markov model, and it's a generative model. Okay? If I wanted to, I could just write print here, and this would basically or I could say generate the data here instead of observe normal LNP. All you've done is written the generative program here. It's just the generative HMM. You type GCC, you run this, and what does the program do? It actually emits posterior samples of the latent states. Okay. All right. No inference, no inverting, no Viterbi, no forward backward. No, you GCC this and you get samples. Okay. There's at least one person that went, which is good because that should surprise you. Okay. And is that surprising to anyone that you could actually write this like this and get? Or does it seem really, really obvious? Obvious? Okay. Surprising? Don't care? Okay. Those are the heavy drinkers back there. Let's hang out tonight. Okay. All right. Okay. All right. So we'll get to the point where we can talk about how to do this. Okay. Being able to do this is actually significant because it does, so you're going to play with a system that's maybe not super fast and won't mix in particular circumstances and will be frustrating. You think, why are we doing this? But in fact, the point of putting this out there right now is that we actually do have a path towards real scalability. It's really exciting with Venture, Probabilistic-JS, which I'll talk about right now, Anglican, Probabilistic-C. The field of probabilistic programming is really, really rapidly accelerating. I'd say it's, now that, UI is still back there, yeah. It's, I would say that probabilistic programming, when did everybody think that Bayesian nonparametrics was too complicated to ever be used ever? It was probably at the beginning of your PhD, kind of. So, all right, so there's, Bayesian nonparametrics, Bayesian methods, they're way too complicated and computationally costly, and you could never use them. That was sort of an opinion held by many, 10 years ago, something like that. Okay, now look at Bayesian nonparametrics. The UI has, 20,000 citations? I don't know, something like that. And Bayesian nonparametrics are used everywhere, even though they're impractically impossible. I think probabilistic programming is just getting on this ramp up. So it'd be a good time to jump on if just saying. Okay. So in these figures, so this is this Probabilistic-C. We're looking at some sort of KL divergence computed between the posteriors of an HMM, i.e. the posterior marginal state occupancy of the HMM, and the posterior actually cardinality of the number of latent classes as a function of wall clock time. And basically you can get good answers on some relatively challenging problems in the order of seconds. Okay? Things that if I were to write these same programs in MATLAB, you wouldn't. I mean, I have written the same programs in MATLAB, and they don't even show up on this log semi-log plot. Okay, it's actually fast and usable. Again, it also opens up sort of an interesting research path to scalability, which is to say that there's also been sort of an interesting combination of systems work and machine learning kinds of work. And these sort of compiled probabilistic programming approaches really touch very, very closely on systems research problems. So for instance, we can write Probabilistic-C as a natively, massively parallel approach to inference. The compilation step when you compile this program actually replaces the main method with an intrinsically parallel routine that stops and waits at observations and does a whole bunch of interprocess communication and whatnot. We can write the program, but in fact, making it go fast is less of a machine learning issue, although there's some research to be done there, and more of a systems optimization research path. So like the amount of time to produce 10,000 samples while running the HMM code that I just showed you on some EC2 instances that only vary in the number of cores, you should actually see performance going like this, but in fact, you see performance tailing off. So this is a runtime in seconds, and again, we can generate 10,000 samples in 10 seconds, something like that. 10, 15, 20 seconds, I guess, 20 seconds. So as the number of cores increases, we don't see a linear increase in the speed. As the number of particles, so this number of particles here is number of processes, number of threads, number of processes technically. You should see that also speed up. So this is the number of processes run, basically the number of independent particles run. Also, systems are optimized incorrectly for probabilistic programming. And we'll return to this. I know this is a little bit too early to actually talk about this, but it remains, the critical part is that you can do interesting inference in relatively short periods of time, okay? And interesting problems. I'm particularly excited about venture, which is spearheaded by Vikash, and you can look at here. It's a sort of a step beyond, and I think it actually has a really, really good chance of actually being scalable and actually usable for very, very large-scale problems. He pitches it as a programming language and platform, a complete stack from stochastic bits all the way up to the programming languages like I'm talking about. It has a slightly different design twist on it. It really stresses interactivity, and that sort of has consequences for exchangeability. It's all about programmable inference. So in addition to what I'm talking about, what I'll talk about has a compositional language for custom inference strategies. So the kind of thing that we like to do when we write inference engines where we do Gibbs sampling on this and MH on this and forward, backward here and variational on these subsets of variables. This language allows you to do that. And it uses a very interesting representation of the running program to give us a real shot at scalability by basically doing very, very fancy execution trace reuse. We'll get into that later as well. The details are that it introduced the directive syntax and semantics, which I'll talk about, and it has tight Python integration. So if you're Python hackers, you might really appreciate the ability to sort of have a language within a language, and Venture allows you to do that. So you can do probabilistic programming within Python and get data in and out and plot easily and that sort of stuff. So Venture syntax inspired Anglicans. The semantics differ slightly right now, but again, what I'm going to talk about today will allow you to basically jump today and tomorrow will allow you to basically jump straight in and work on Venture programs if you want to, or church programs. So although I'm going to talk about a specific syntax, I'm not really doing you too much of a disservice because the concepts and even the programs more or less can be directly transcribed between the three languages. So basically, time invested in Anglican is not a waste, even if Venture is the language or Probabilistic-JS is the language or whatever. Okay. Have I been going for 45 minutes? Is that right? About halfway? Is it just so horrible that nobody actually can answer the question? Is that right? Okay. Okay. All right. So it's kind of an interesting exercise teaching a language and an inference simultaneously to a group, because of course what I need to do in order to teach you the language is put up a bunch of really horrible slides on syntax, right? Then you can start programming the language and so on and so forth, but you can just read that stuff yourself. The other part is kind of harder. It doesn't seem related until you go back and think about it later. So before I give you the horrible syntax slides, which they're coming, let me introduce you to sort of a problem template or a way of thinking about what probabilistic programming can do that's maybe a little bit dissimilar to what you think about in terms of statistical inference, writing down a mathematical model of some phenomena. Okay, so there's a problem template that you just keep in the back of your head, file it away. Maybe you'll think of it again in 3 years or something like that. Imagine that you're in some sort of problem domain. This has come up again and again and again since we've actually written Probabilistic-C, but we've been thinking about this for a little while. Pretend that you want to write some deterministic simulator, or you have a deterministic simulator of some phenomena. Okay? Some crazy function that takes some set of parameters, maybe the geometry of the world, and pushes it through a renderer, or some sort of weather simulator, or some sort of, well, I'll get to some examples. You have some sort of deterministic simulator, but it's written as code. Somebody who's not natively probabilist or natively Bayesian says, I'm just going to model this phenomenon, I'm going to write some generative code. Okay? It's probably going to be wrong, but I'm going to do it. Of course, they don't really actually know what parameters to this code they need to use usually, or because like you don't know how to get the simulator to actually match the observed quantity of interest. But okay, make some decent guesses. Okay. Then, after you have this deterministic simulator, you actually do some sort of observation. Maybe you actually see the scene that's been rendered, or you measure some engineering phenomena related to the output of this process which you've modeled. And the question is, how do you update your estimates of what the parameters were that went into this simulator, these parameters of interest, and how, for instance, do you use such a simulator, whatever it is, sort of a black box, to do posterior predictions? In other words, you've made some sort of observations, now say something about the state of the world as it is to come. Okay, let me give you a sort of a fun example of this. When I started talking about this at Oxford, the head of the engineering department came to me and said, "Whoa, man, you've got the solution to my problem." Okay, very strange because you're a civil engineer, and I don't know anything about civil engineering at all. But to be perfectly honest, his name is Guy Holsby. Anybody know Neil Holsby by any chance? No, you must know Neil. Yeah. Okay. So Neil is a student of Zubin Ghermani's, or was. Guy is his father. He's the head of department. I'm going to solve his problems. Okay. So Guy is the world's foremost expert on the performance of jackup units. Anybody know what a jackup unit is, other than that picture? Okay. All right. So what are these things? They're big. They're really big. They sort of go up and down on these posts. They sit on things called Spudcans. Okay. Things like the geometry of the Spudcan are kind of unknown. You have a bunch of guys welding it. Don't actually really know what size it is. There's some engineering tolerances in all of these geometries and whatever. Of interest, perhaps to you, certainly of interest to the oil industry, is that there are about 400 of these in the world. They cost on the order of 400 million currency units, whatever that happens to be, right? Millions of currency units. And the industry suffers a total catastrophic loss of one of these once every 2 years. Oops. Okay. How do they work? What do they do? So you float these things out to whatever site you're going to do drilling or some sort of operation. You lower the legs. Then you put it in what's called light ship load configuration. You jack the platform up. It's heavy. It's made out of steel. Weighs a lot, right? And then the legs get punched down into the ground. Okay. Then there's things just like compartments that you can pump water into. So they make it really heavy by pumping water into it, which drives these legs further into the ground. Then they dump out the water. They climb up the legs all the way to the top, and then they hope it doesn't tip over in storm loadings. Okay? Okay, so just think about it for a second, right? So you know that when it pushes down, you're going to get what are you going to get? Okay, so beforehand, you're going to get some sort of civil engineering-y kind of measurements about the strata below where you're going to shove these legs in, right? Then you're going to get a couple of measurements at light ship load. So in other words, you can actually see how far they penetrated. Okay. Then you're going to get some measurements here at preload. You're going to see how far they went in after that. And then what you want to do is, using whatever simulation you have or whatever understanding of the physical world, obviously when waves come, they're going to exert downwards force on the legs, right? And you need to know what the load-bearing capacity in that direction is in order to know whether or not the thing's going to tip over. Yeah? Okay? So it turns out that that the soil mechanics, I know nothing about this, absolutely nothing. Okay? The soil mechanics that, I won't go backwards because that will take forever, that when these things go in, it actually matters what the shape of the little tip is and what the dimension of the Spudcan is and what all of the rock layers are and so on and so forth. And there's a whole bunch of if statements, like if this tip is just touching, then if the triangle has gone, then the soil mechanics behave in this way, then as it's in but not all the way up to the top, then there's something else, and then there's, if it goes below, then there's some sort of additional overburden capacity that gets added into the strength equations, blah, 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 okay? So Guy, bless his soul, actually wrote a deterministic simulator for this system as code, okay? It's used by the oil industry. That's what they use. It's about 750 lines of C code. Actually, what was it originally written in? Euro? Doesn't really matter. Yeah, I wrote it in Visual Basic. Okay. We did him the slight favor of translating it over to C code. And it's got a bunch of parameters having to do with sort of the uncertainties in the geometry of the Spudcans that are being shoved in, uncertainties about the performance of various rock layers, uncertainties about all kinds of stuff, okay? It's this black box routine, okay? It's just a big chunk of code. I've looked at it. The code's not that pretty. I think you'd probably agree. It's not that pretty, but it's the standard. It's the thing. It works, okay? And it's not differentiable, right? You can't plug this into Stan, right? There's a bunch of ifs and whiles and grossness, okay? And Guy, being a very, very good engineer, he says, actually, I really don't know for sure whether or not my parameters are right. So I'm going to write a deterministic simulator, which gives me this red line. I just execute the code. So I've got code, and I've got parameters, and I get an output. The output is this red line, basically. Okay. Now I say, well, I actually don't know what the geometries are and all that sort of stuff. So I'm going to vary those, and I'm going to get a stochastic simulator. And I'll do the right thing. I'll put some probability densities or distributions on the parameters and then vary them. And I'm going to get a distribution over the output of the simulator given the prior distribution on the parameters. Okay? So that's, we add a couple of hundred lines of C code that puts priors on the parameters, and now we have a stochastic simulator. And then the question is, what do you do when you actually go in and you see what happens when you get data? Like, what's going to happen? Like, if you get data here and here, what does that mean? Does it mean that are we over here, which might be totally stable, or are we over here, which might be not good, right? So in other words, if we're over here, if you add load, it's going to penetrate much more quickly than over here. See, this is penetration depth versus measured load. Okay, so what you don't want is you don't want the thing to penetrate too much. Excuse me, because it will the thing will tip over. Okay, so with adding on the order of tens of lines of Probabilistic-C around this, we can just automatically invert the whole thing and get thousands of samples a second, which gives a posterior distribution on the performance of the machine given the first three observations and the last ones, and so on and so forth. Okay, and that's pretty cool. What's even more cool is that we get a refined posterior on the parameters of interest. Okay, so again, these guys are not statisticians. When we see data like this, we have depth, and then we have undrained strength, which is some sort of basically the strength of the underlying soil. There's an obvious change point here, right? As you go deeper, there's some change point in terms of the material properties, and then that maybe there's a rock layer or there's a sand to rock transition or something like that. We would see this as a change point model. They code this in their simulation and represent the uncertainty as basically what the slope is and where this is and what the slope is. They don't actually code it as a change point model. It's not an inference problem. There's just an answer provided by an expert plus some uncertainty about it. So the answer, for some reason, the expert decided to say that was the fit to this data. In other words, this is the strength at depth, the black line. I would argue that when we did posterior inference in this probabilistic programming sense, and in fact, Guy also agrees that the interpretation of the data, even without access to the change point model, without access to these dots, actually, is a better representation of what's going on here in this data. Anyway, okay. There was a very nice paper on inverse graphics that came out at this NIMS. This paper actually fits the exact same kind of template. Okay, so you have a generative scene model. So in this paper, so Yura is on this paper as well. Vikash is the first author. in this paper, basically you posit the world as the uncertain parameter. The renderer is the deterministic simulator, and you use probabilistic programming to do automated inversion of that. So you're not going to differentiate the renderer. It's low rank. So you can solve this using probabilistic programming as well. So there's some beautiful example applications. I think probably the most compelling in probabilistic programming today, where they used this technique to solve CAPTCHA by positing a generative model of the scene, basically placing characters down, so on and so forth, then rendering that scene, which basically composites an image and compare it to the observed output. Inverting that process solves CAPTCHA. You should read the paper, it's awesome. Same thing here. If you try to do road finding, say for instance for an automated car, or a driverless car, then what you might want to do, a natural way to solve the problem, if you're thinking in terms of probabilistic programming, is to build a world model that consists of roads and not roads, and its geometry, render it, and then compare it to the output. Then invert that process automatically. Okay? It's a style of thinking thing that I'm trying to get across here. And the fact that there's some sort of programmatic, we know how to write renderers, but a renderer is really a program in most cases, right? Particularly when you have to do Z buffering and that sort of stuff. It's a little bit complicated. Okay. Questions at this point? That's a lot of sort of salesy kinds of stuff, actually, I know, but we'll get into it in just a second. Questions? Comments? Concerns? No? Okay. So then we'll move on and get into the basic probabilistic programming concepts in this Turing-complete family. Procedures, sample. Okay? So a deterministic procedure, you give it an argument, it produces a value. Okay? And in Turing-complete probabilistic programming, the kind of probabilistic programming I'm going to talk about, procedures, sample. You give them arguments, they return samples from the distribution induced by that procedure. Okay? Deterministic functions, deterministic procedures, are sampling routines that are very boring. They return the same sample every single time you invoke them. Okay? If you get that, that's basically it. Go. Okay? What this really means is that programs are generative models. Okay? You don't actually know what execution path your program is going to take or what every procedure is going to return on every execution, but you write variable declarations, you write all of your procedures as samplers, and the program is just a sampler, basically. It's straight up a sampler. It's a generative model. Okay? But because it's a programming language, okay, so we're not just writing a generative model in the standard sense, right? You can have mixed deterministic and stochastic procedures. You can write any kind of procedure you want. It's not generally differentiable with respect to parameters. You can write ifs and cons, and you can define functions, and you can evaluate those functions, and you can write program text, you can generate program text, you can do all sorts. Anything that you can do in a programming language, you can do here. There's not generally a factor graph correspondence. You can write programs that correspond to programs that are differentiable with respect to all of their parameters, or you can write programs that correspond to factor graphs, but that correspondence isn't guaranteed. So we can't use sort of special case inference algorithms over the entire program execution trace. Of course, these programs may have non-deterministic random variable cardinality. And tomorrow, I'm going to give you one little exercise which will stretch you a little bit, I think, with respect to that. Okay, so writing probabilistic programs. I'm going to talk about syntax and semantics. So the syntax of Anglican and Venture, or share basically these three directives, and even this one I believe is currently called sample in Venture instead of predict. They also have predict, but it doesn't matter. There are outer directives and inner expressions. Okay, so the outer directives, the ones that really actually matter, are assume, observe, and predict. And all of these things, symbol, expression, expression value, expression, they're all expressions. Okay, so they're arbitrary pieces of code that, when evaluated, return either a symbol or some arbitrary expression or something like that. Okay. Roughly, I'll say this again, assumes are basically random variable declarations. Okay. So this is basically going to be some variable. This is going to be a procedure for generating it. Okay. Observes take some expression, which also is a sampler in some sense, right? Which is every expression is a generator. It's a sampler, right? So this is a sampler, and it constrains the output of that expression to take this value. Okay, and predicts the value of an expression. Okay, so you might put a variable name here, and predict will give you an output of the posterior distribution of that variable. But you can write arbitrary pieces of code here as well. So you can compute functionals of your latent variables intrinsically. We have a couple of little helper directives that you'll find useful as you're doing stuff. Observe CSV allows you to inject a very large number of observed statements directly in one line, and import allows you to import a bunch of directives from external files, either on the file system or on the web. Okay. The expressions, this is where the fact that 2/3 of you have some experience programming in Lisp, this will be extremely helpful, and I can go through this relatively quickly. Again, I would stress, I hope you can see this, there is a website here, my homepage /Anglican/language, which has a language description and should be actually quite helpful as you're working on the practical exercises. Expressions can either be literal, symbols, or lists. Oh, I should also say that if you are in a group or you're going to group up on in the third lecture, make sure you have somebody who's programmed in Lisp in your group. Okay? So expressions can be literal, symbols, or lists. The literal can be a Boolean, a long, a rational, double, a string, or lists are the fundamental thing. They can either be empty, or they can consist of a keyword and some arbitrary set of expressions, or they can consist of a procedure that's going to be applied to some arbitrary number of expressions. And keywords include quote, define, lambda, if, cond, let, and begin. So quote yields a quoted expression. It actually allows you to manipulate program text in some sense. It yields an unevaluated expression. Okay? Lambda is how you create procedures. Okay, so functions are first-class objects in all the languages that I'm talking about. So lambda and some arguments, or lambda and a single argument, plus a body, which is going to be some set of expressions, constructs a compound procedure. So for example, defining this anonymous function lambda of 2 parameters n and m says that this procedure does the following. It adds 1 to n, and then multiplies the result of that to m. And how do you evaluate a procedure? Well, this is a procedure. We have constructed a procedure here. It's an anonymous function. Okay? Now we can run this or apply this procedure to these arguments. So this means the outer parentheses. If you remember, I said that you could have a procedure here. So lambda creates a procedure. Great. Now we have a procedure sitting there. We can apply that procedure. So a procedure, when you apply it to its arguments, actually runs the procedure with those arguments plugged in, which says that it's going to bind n to 1 and bind m to 2. So if you add n plus 1 is 2, times 2 is 4. Okay? If is how we introduce control flow. So the expression if, predicate, consequent, alternative. Okay? So all of these are expressions themselves. So you can see this is some big context-free grammar, right? Or grammar, I should say. So for example, the predicate here is always true. If equals 1, and if 1 equals 1, then the predicate is true. Otherwise, the predicate is false. Okay? So evaluating this if, this expression returns the predicate is true, the string. Okay? Easy enough. Cond, let, and begin are quite useful. Cond is a switch statement, basically. So it allows you to check multiple predicates and evaluate the corresponding consequent all in a row. And if none of the predicates are matched, then it will evaluate the alternative and return it. Let allows you to locally bind variables. So this is quite useful when you want to we'll get to it in just a second. I think maybe even, nope, not the next slide, but there is no set. You can't redefine variables. Okay? There's a good reason for that. So sometimes you want local scope for variables, so let blocks like this allow you to assign a the value 1 regardless of whether or not it was defined, because these are local bindings to the let block, so you can say a1, b2, do something, print this out, and then add a and b and return that value. Okay? And begin allows you to concatenate a large number of expressions and have those expressions evaluated in sequence. There are lots of primitives available. Again, check the documentation, nil, sum, blah, blah, blah. There are relational operations, most of them that you would expect, and or not equal, equal. There are types. We try to hide this from you a little bit, but there are longs, doubles, booleans, strings, and read strings, so you can cast between them. List is the fundamental object like in Lisp, so you can get the beginning and the end, the first, the second, the nth. You can count the number of bins or elements in the list. You can stick them together, and you can ask how many unique elements there are on the list. You can do arithmetic, and of course there are tons of math operations as you would expect. The core procedures, things that you can do straight away, include being able to evaluate an expression. So if you have a quoted expression here, this is any string, right? You can evaluate that string. It's like eval in MATLAB, okay? But it's really fundamental to the language here, okay? So it takes the expression and returns the value of evaluating that expression, okay? If you don't quote this, then what happens? If you don't quote the expression, then if you have a parenthesized thing there, it will interpret that parenthesized thing straight away, and then it'll eval a constant or whatever the return value of the non-quoted expression is. So quoting is kind of important. That's how you say, this is program text. If you don't have a quote there, then it evaluates the expression directly even before it gets passed to eval. Think about that for a second. It's kind of important. Apply proc args allows you to, for instance, dynamically construct a procedure and apply it to a list of arguments. Okay. Okay. So the interplay between these two is pretty important. Another core procedure that's really important is mem, which is a functional. It takes a function, returns a function. Mem takes a procedure, and it constructs a memoized procedure instance from an expression proc that must evaluate your procedure. So proc can be a procedure as well, but it must actually evaluate, or an expression, but it must evaluate to a procedure. And what does mem do? It basically wraps this proc function the way you can think of it. It wraps this proc function in a hash map that basically looks up the same. If you call the memoized version of this proc with the same argument twice, it will not redo the computation the second time. It will just return the cached value. Okay? So this is actually really critical in probabilistic programming systems without set, or in Lisps in pure functional Lisps, because this gets us both dynamic programming for free. Basically, you don't want to redo computation that you don't need to. But it allows you to sort of incrementally, lazily construct complex data structures. Okay? So here's an example of how you might use mem to do something nice for you. Maybe if you're familiar with, say, for instance, Chinese restaurant process and you want to build a base distribution, you might want to do something like this, where for some, so basically H is going to be a memoized procedure of one argument K. Okay, so this is a strange construct, but it's actually kind of important to get, which constructs a list consisting of a draw from a normal distribution with mean 3 and standard deviation 4, with the second element being a draw from a gamma distribution with parameters 1 and 1. Note that K is not consumed by the procedure here, but that's okay. It's fine. The K here is basically for the mem part of this, which is to say that if you call H then with the same argument twice, it will compute this the first time. In other words, it will go off and make these random draws. It will execute these procedures, which return random variables. But the second time, it will look up the value in the cache, not re-execute that part of the code. Okay? So assume theta 1, H1 gives you a value for theta 1. Assume theta 2, H2 gives you a value for for theta 2, assume theta 3 h1, and then if you predict whether or not theta 1 and theta 3 are equal, this will always return true. Everybody get this? Any questions? Yeah. 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 Any other questions? You're going to see this. I put this a little bit early because you're going to see this a lot in the examples. This paradigm for lazily constructing data structures, essentially. Okay. All right. So I showed you a couple of elementary random procedures before actually talking about them. You can write. So I said every procedure is a sampling procedure. So you can write sampling procedures. You can write generative procedure. You can write whatever you want. But we provide you with some, and there's reasons why we need to actually provide you with some. Really, all we need to provide you is a random bit. But it's convenient for you that you don't have to write beta and binomial and Dirichlet and whatever. So beta allows you to draw a sample from a beta distribution with pseudocounts A and B, binomial, categorical, Dirichlet, discrete, exponential, flip. Okay, so this is a random bit. It's a weighted coin, basically. This sample from a binomial trial returns true with probability p and false with probability 1 minus p. That one's actually pretty important. Gamma, inverse gamma, normal, all of these things exist. Poisson, uniform continuous, also kind of useful. So if you want a rand, it's uniform continuous 0, 1. Okay, you could define that in your own library if you wanted to. And uniform discrete, min max, you should pay attention to this. In the discrete set between min and max, it samples from min to max minus 1. Okay? So these are procedures that are provided to you if you use them. When they're executed, in a particular, every time they're executed, they sample. They'll give you a different value out. Okay, semantics. Assume. I already said this, but it was worth saying it again. Declare variables. You can think of it as define in some sense. So you can declare variables, random and otherwise, non-random. Observe data. This is how you introduce data and constraints. And predicts are the posterior functionals to report. Okay? So running Anglican is about as easy as it gets. The command line switches, and there are more of them than this, and there's a little bit of in and out burger. Who knows? There's a lot of Europeans here. Who knows in and out burger? Okay, those must be the Americans from mostly the West Coast. Sorry about that. So there are these obnoxious restaurant chains that have special menus. I think, I find it really, really obnoxious. But we do kind of the same thing, the special menu. If you know some of the command line flags and some of the things that, there's more to it than what's there, if that makes sense. So if there are things you want to do, quite often there's extra stuff there. Did that make any sense to anyone, what I just said? No? Okay. At In-N-Out Burger, there's like 3 things on the menu. You can go in and you can order just random stuff off a secret menu that they know how to make, but you have to know what the names of the things are. Okay? It's really obnoxious. We have a little bit of that going on. So there's a couple of primitives that exist that we don't put out there because we don't know what, they're kind of secret, so on and so forth. I'll reveal a couple of them. There's a few command line switches like that as well and arguments to them. There's good reason for that. We haven't fully tested them. And also, as you'll find, probabilistic programming systems allow you to, as I would say, shoot yourself in the foot fairly straightforwardly, fairly easily. So we try to minimize that in a number of ways in Anglican. So you can get help by invoking the Anglican with a help flag. The critical ones are, the ones you'll probably use are -s is how you import, is how you give Anglican a source file to run, and -n, which is the number of samples you would like it to produce. If you don't specify -n, the calling semantics of Anglican produce a stream of output predicts that goes forever. If you don't know how to use Control-C, learn. Okay? As you can tell, I have white hair. Growing fat. I'm old. I'm a Unix guy from a long time ago. So think Unix hacker when you think Anglican. You're going to use shell scripting. You're going to do all sorts of stuff. You can put it in pipes. You can do all that sort of stuff. Think Unix, Linux, Mac OS, whatever you want to think. How you run it. That means if you run Anglican with no arguments, it will just sit there because it's waiting for code on standard in. Okay? Do not be confused by this. That's probably the number one thing. You'll type Anglican and be like, nothing, okay? That's expected behavior. If you want it to run a file that you've saved somewhere, type Anglican -s. Or, because it's Unix, you can just take whatever source file you have and cat it into Anglican, and it will start producing samples. Okay, so if we want 1,000 normally distributed samples, we just do that. Okay, so let's do that real quick. I apologize. You should be aware that because it's Java, the JVM starts up. Because it's Cloture, then there's a bunch of stuff that happens. So there's always about a 4 or 5 second lag before things start. That has nothing to do with Anglican. It has everything to do with the system that it's built on. You could set this up so that it's permanently resident, and you just pipe commands into it. But that's too complicated to set up. OK, so that's horrible, right? So you can't actually see what's happening. It just generates a whole bunch of samples. 1,000 of them, in fact. How you deal with those samples is kind of up to you. We've provided a couple of scripts, though, for you that are kind of useful. What ends up happening is basically whatever predict statements in your program, Anglican emits a stream of samples that if you average against, give you proper posterior averages. So that's the predict statement. This is its execution value in a particular execution trace of the program. And if, say, for instance, you then take and run this compute moments script, it will look for all of the unique output lines and then actually compute the moments of them. So this is nice. The expected value of the predict statement normal 510 is 4.93, and its variance is 100 as you would expect. Does that make sense? Questions? Okay. So it's pretty easy to write expectations and to write functionals. You just write them as whatever kind of script you want. You can consume this however you want, right? If you want to compute the probability that mu is greater than 7, how would you do that? You just write a little script and ask whether or not the second argument is greater than 7, and it's going to and then count up the ratio. Okay. I'm not going to do that. Anglican encourages you, and all of these programming languages encourage you to think generatively. So think for a second. How would you write give me some idea, a generative program for answering this question? Approximately, I mean, everybody knows the birthday problem, right? We know that with high probability, there's a pair of people in this room that share the same birthday, right? Okay. So how would you answer that question generatively?
Generate a list of random numbers from 1 to 300 and then compare.
Okay. Yeah. All right. Great. So that's exactly what we're going to do. So we're just going to answer this question generatively, right? So the question is, okay. So for everybody, we're just going to for however many people there are, we're going to specify a generative model, right? So here's a generative model. Mem lambda I, uniform discrete 1 to 366. What does that mean? Every time you call it with an index, it generates a birthday for that person and then remembers that birthday. Okay? We assume that there are 23 people, for instance. Okay? And what we want is we want to know whether or not basically we want the probability. We want to know whether or not there's a pair of birthdays that are equal in the room, right? And the hard part about this is actually not the generative model, but it's actually writing down the predict expression that we care about, okay? So this is sort of the first piece of code, right? So assume pair equal is a function that takes 2 arguments, and basically what it does is it looks at the upper triangular portion of a pair matrix. If I is greater than n, then we return false. If j is greater than n, then, well, we either go down a row or we check if the 2 birthdays are the same. And if the 2 birthdays are the same, then we can we can return true without evaluating the rest. Otherwise, we go on. So we can run this pretty easily. I'll just show you this so you see what kinds of things you can do. Let's see, echo. We should probably specify a number of samples here. How many samples do we want? Doesn't really matter. Do 100 samples. Okay. The output from that is not that nice, so we can use the another script that we provided you, which allows you to just basically count the. So this says it counts the number of times that pair equals occurs in the output, taking value false. It counts the number of times that pair equals 1, 2 equals true. And we can see that basically in a room of 23 people, the probability that 2 people share the same birthday is around 50%. Okay? Okay, so this is advertising a particular style of, so, yeah?
Just this normalization, what's the scope of this? Is it only within one sample? Because I mean, you have the sample. I got function birthday. Would you remember the birthday of the person?
So the question is, what's the scope of mem? And that's a very, very, very good question. The shorter answer is the shortest. How to answer that concisely, given that I have a couple of things that I want to say. The scope of mem is the execution of the program. Don't get confused about what happens in inference. There's a program. If you were to run this program once, the mem is correct for one execution of the program. You can think of this as define, 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 print. It doesn't memorize over. Don't think, oh my God, you're running the program many, many times. There's something crazy going on. Mem could be doing something funny. It's just the scope is here. Is that fair?
Okay, this is executed once per sample.
Not quite. Okay, so the comment was basically this is executed once per sample. It's both true and not quite true. Okay, so why purely functional Lisp? Okay, you guys are probably, anybody who's a programmer will think, why are you doing this? Why are you making us do Lisp? Oh my God. Well, you don't have to. I showed you that you can do Probabilistic-C or probabilistic JavaScript or whatever. There's other languages that are coming to fruition, but it's the shooting yourself in the foot thing. Purely functional means no set, okay, basically. And there's an exchangeable argument evaluation thing going on as well that's interesting. But it basically prohibits you from doing something like this. If you assume A is normally distributed, then you assume B is normally distributed with some parameter A, and then you assume A is normally distributed with some parameter B. Can't do it. Don't want to do it. In other languages, you would be allowed to do something like this. You can do variable reassignment without special consideration. And if you do this, then you end up with this funny sort of problem, which we want to avoid at basically all costs because this doesn't make any sense. Okay? All right? So it's the purely functional part. It's this no variable modification thing. So we could be here, and we could, in imperative languages, we can achieve this by basically saying that in fact this A is a different random variable than this A, but then things get really complicated and the semantics of the program don't correspond to your intuitive understanding of what the program should do given its text. Okay? Does that make sense? Okay. Okay. So how about imposing some soft constraints? Let's do approximate Bayesian computation actually, but I didn't say that. Okay? So what if you're asked to say what numbers, when added together, equal 7? How to do that? Let's think generatively. Awesome. Somebody else, give me a program, quick. Yeah, okay, this is the dumbest program ever, right? But it's absolutely, totally fine. If you're thinking generatively, you just start sampling a number. I mean, if you ask a kid to do this, how would they do it? What numbers before they actually have it's questionable. I actually don't know I don't know the answer to that, right? Maybe they just start 5. 2, So we just pick some numbers. Okay? So obviously, no kid is going to think I'm going to draw a Poisson distributed random variable with mean 100, then subtract 100 from it. But that's some code, and it generates some crazy number A and some crazy number B. So Anglican prevents you from shooting yourself in the foot in one other way, and maybe we'll get into it a little bit tomorrow. I sort of doubt it. But in Anglican, unless you consult the in and out menu, the outermost procedure in any observed statement must be an ERP. Okay? That is to say that this thing actually must be a sampling procedure. And this is going to cause some it'll be a little bit cumbersome for some of you as programmers. But a soft constraint would be to say that this sum of, so that we're going to observe a normally distributed quantity whose value is 7, whose mean is the value of adding A and B together. We're going to impose a little bit of noise, and this basically takes us from satisfiability, a really sort of combinatorially hard, NP hard kind of space, to a space where there's enough softness for us to actually search for and find a solution. Okay? Then we'll just predict the list of A and B. So we can do that just for the fun of it. It's kind of, why not? You can do it. Let's do 1,000 samples just to see what comes out. Oh, we don't want the. Did I do that? Thank you. Let's do 1,000 and let's do compute. Did I do something wrong again? No, I don't think so. All right, so I get some answers. Yeah, okay. So there are the machine hypothesizes a bunch of numbers who, when you add them together, not surprisingly, equal 7. Although it will make mistakes. If you have it draw a million samples, it will make a few mistakes. And if you decrease that or increase the noise level, it will make many, many more mistakes. Okay? All right. That makes sense, I assume? Yeah. All right. Okay. Okay. Question, why didn't you draw from a uniform? Doesn't really matter. And even though I do want to get through a couple of things, one of the key points, and I thank you for asking that question. We should ask that question a lot, right? This actually gets exactly to the point. Maybe I should just talk about this and not actually do the rest and just finish up the rest next time. The question was, why wouldn't you use uniform? Okay. Well, in this case, there's no reason. I can modify the code like that. Okay. Now, if you were going to write the inverse instead, if you were like, say, for instance, writing a rejection sampler for something like this, you'd actually have to change your entire sampling code, right? Okay. So iterating over models, answering questions like, why the heck are you using this crazy distribution over numbers instead of a uniform distribution? Well, we can just iterate and see which one does better. Maybe the uniform one actually gets a broader selection of answers. Who knows? Okay, but we can iterate quickly. Okay. Okay. How do we observe data and actually do proper Bayesian inference? So the simplest thing that we can do basically is assume we want to get a Bayesian estimate of the mean of a Gaussian distribution given some observed data, right? So let's assume standard deviation is square root of 2. Assume mean is normally distributed with value with mu. It's going to be the unknown mean. It's normally distributed with mean 1, and variance is square root of 5. Let's observe that a draw from a normal distribution with that mean and that variance, standard deviation, excuse me, took value 9. Let's observe that a draw from a normal distribution with that mean and that standard deviation took value 8. We can put as many observers as we want to here, right? And we want to predict mu. Okay? So this is going to do posterior inference, okay? So when we run this program, Anglican will output a stream of predicts, like I've just showed you several times, which are the posterior values of mu given the observations. Okay? Cool. If you take expectations with respect to those, so mu here is the parameter of interest. So as this set of samples goes to infinity, this empirical average will converge to this expectation. This is really saying that basically any predict that you do will converge to this expectation. And in fact, it doesn't matter. Predicts are arbitrary expressions of your program state. And the limit, the empirical limit of these predict statements will also converge to, any of these predict statements will also converge to the posterior distribution of the predicts under the posterior distribution of the model parameters, the program parameters, given observed data. So this is going to be observed data, and these are program parameters. Okay, maybe what I'll do, because I know I'm out of time, although I started 4 minutes late, I will come back to the church and venture comparison just to give you a sense of how Anglican looks compared to these two languages, starting first thing in the morning, and I'll talk about limitations as well. But what I'd like to do right now, just to finish and to make you realize that maybe there's actually something here besides doing really, really trivial inference problems and solving problems that we could all solve pretty straightforwardly. Well, we can all solve these, but there's something a little bit interesting going on here. I'm going to race the computer, I think, if that's OK. Give me a second, because I need to start the computer, because it's unfair right now. Let's make sure this actually runs. OK. Go like that. OK. There are 138 of you, or however many, so I needed to start the computer a little bit early because you've got parallel processing going on here. OK. So the examples that I've given so far are basically just pedagogy. They're just, this is how you actually code, right? This is how you think about what you're doing. You write a generative model, you constrain it, you get a posterior distribution over the program state, basically. Okay. So Andreas Stuhlmuller has a very nice example on forestdb.org, and this has appeared in the literature in a number of places. His supervisor Noah has something, Vikash has something in his thesis, so on and so forth. But the example came directly off of ForestDB, which has a bunch of really mind-warping uses of probabilistic programming. I think that's really, really interesting. We have been focusing on inference. Those guys have been focusing on inference and use, and their use cases are really awesome. So here's the question. Probably you've already figured this out. What's the next number in the series? Who says 3? Who says -1? Okay. What's the expression? Got one alternative here. Anybody else want to? Everybody see the expression or no? I think I'm hearing 7 minus 2 what? 2x? Okay. Everybody likes 7 minus 2x? Okay. All right, so what have you done? Okay, so you can more or less get the pattern. You can do some sort of regression, okay? But what I just asked you to do is a little bit more interesting, right? I asked you to do inference over this space of expressions, of mathematical expressions that could give rise to this relationship, right? Okay? Everybody understand that this is fundamentally different than just solving the regression problem, right? Right, okay. Okay, so I think you guys came about the same speed as the computer, okay? Oh, there it's hallucinated something else, okay? Okay, so what's going on here? So I'll scroll up to the top so you can see what's going on. And then this is basically it. I'll come back and we'll do this again next time. Okay, this is not at the top yet. The computer is very, very good at hallucinating. I want to say that out there. It must have done a lot of mushrooms in its earlier life. But okay. All right. So I started the program, racing you guys, gals, people, and basically gave you the problem of observing that there's I'm going to do a soft constraint with some sort of noise here, that the induced procedure, whatever this procedure is, evaluated at the input value 1 produces 5, evaluated at the input value 2 produces 3, and evaluated at the input value 3 produces 1. Okay? The parameter of interest is the procedure itself, the code. Okay? Right? So what we're going to predict is a list. I changed this so that they're on the same line. We're going to produce a list of the induced procedure code, the actual code itself, and the value of running that code on the new output, on the new input. Okay? So we started off and it produced some procedures, lambda x plus 5, 0. Well, there's no x in that. It's pretty obvious what that procedure does. It produces 5. Let's see, lambda x plus times x0, 5. Okay, so it's trying a bunch of stuff and it makes a bunch of mistakes in the beginning. But by the time you guys figured out the answer, it started, it's trying a bunch of stuff. 5 is pretty good. Then all of a sudden, it arrives at a much more plausible solution. The procedure is 2 times x minus 7 gets the right answer. It still actually thinks for a second that there's a possibility that dividing 5 by x is the way to go. Okay, that's better than 5 in terms of an output, but it's still not right. Right? And then it just starts on its merry way. It says, okay, well, actually, if I add 0 to x, that's fine, and then multiply that by 2 and subtract 7, that's okay. It still is okay. And now we're actually developing a posterior distribution over procedures, right? And that's pretty different. And I would say that that's kind of interesting, right? I would argue that this is kind of important if we are doing the AI thing. Okay? So is this the right procedure? Nah, probably not. But the ability to do inference over the space of procedure, the ability to do inference over the space of code is pretty fundamentally different, pretty fundamentally unique to probabilistic programming of the Turing-complete kind that I'm talking about, and I think really very, very interesting. And I'm finishing now, I promise. I know I'm running over. Let me just say the following. So for tomorrow, we'll go over the solutions to these in person. There are 2 very simple, I shouldn't say very simple in case some of you have trouble with them. There are 2 relatively straightforward. That's probably also bad. There are 2 exercises that I think that you can do even while hungover for tomorrow, one of which is automatic Bayesian inferences programming. So if you go to this link, Teaching MLSS 2014, then the exercises, the first 2 are the ones to do. Automatic Bayesian inferences programming, and then a short exercise on this procedure text as the inference objective, entitled "Things Turing-complete probabilistic systems can do that others can't." Try those out, and we'll dig in even further tomorrow. So, thank you very much.